we spend a lot of time explaining the concept of the limit of a function as x approaches a number c, right? And we are coming to our next big concept, is continuity. When can we say a function is continuous at x equal to c? So mathematically, the requirement is, first of all, the limit of f as x approaches c needs to exist. So let's just say the limit exists and equals a number, okay? And let's call this number L. And the second condition is that limit c must equal f of c. So when I write this notation, I already mean that f needs to be defined at x equal to c, okay? So if f is not defined at c, for example, if I have f of x defined as 1 over x minus 1, then this function is not defined at x equal to 1, because when x equals 1, you have 0 in the denominator, and that's not cool. So this function is not defined at x equal to 1. Therefore, I can never ever write down f of 1 for this f. So this notation does not exist. Okay? So when I write f of c, I automatically imply that f is defined as c. Otherwise, this notation f of c does not make sense. And in addition to f is defined as c, I want L is equal to c. So if I replace L by the limits, by the limit of f, in short, I can write all the three conditions. Okay, so 1, 2, 3, basically, all together in this line. Okay, so first the component is the left-hand side needs to make sense. Second component is the right-hand side needs to make sense. And the third component is the left-hand side must equal right-hand side. Okay? So we're gonna use this example to see what that means. Okay? So we're gonna look at these graphs and see for which function f we can say f is defined at x equal to c. All right, here we go. So in the first graph, do we have f of c? So yes, we do. F of c is defined. It's that value. Okay, the height is at this point is f of c. So we have f of c. Do we have the limit of f as x approaches c? The answer is no, because in this case you have different left and right behaviors. Therefore, this condition fails. Okay, does not exist. So therefore, we say this is not continuous. Let me just use CRT at x equal to c, just for this point only. Okay, 1, it is not continuous at x equal to c. Why? Because the limit of f as x approaches c does not exist. So if you look at the 1, 2, 3 components, component 1 fails. I have component 2, but component 1 fails. If any of those 3 conditions fails, then I cannot say f is continuous at c. All right, so here I have f of c right over there. So I do have f of c is defined. So that's cool. Now, if you look at the graph, would you say the limit of f as x approaches c exists or it does not exist? Think about the definition of limits. So this will be talking about as x approaches c from the left, what happens to the associated f value? So the associated f value is the height in the y-axis. So it goes this way, right? So the limiting value seems to be like whatever that empty circle is. And you also look at what happens when x approaches c from right to left, okay? So the corresponding f value goes this way. And you can see they're gonna meet at the empty, where the empty circle is. So if this is height L, then we do have the limit exists and equals L, okay? So I also have condition 2, okay? So let me label them. F of C is condition 2, so condition 2, check. Condition 1, check. Now, if you look at the graph, you can see that f of c is not equal to the limit L. So condition 3 fails. Therefore, for example 2, function is not continuous at x equal to c. Okay? I hope you're getting the idea. I have one equation down here, but every single component must hold, must make sense. If any of this fails, then I cannot say f of x is continuous at c. All right? So let's move on to the next one, number 3. Do I have f of c? Well, by looking at the graph, you can see that the function values becomes like larger and larger, but it's never being defined as c, so it's not defined, so I don't have condition 2. All right, so basically I'm done. I can already say that for this case, we cannot say f is continuous at x equal to c. Okay. Furthermore, in this case, even though we know the limit is infinity, but infinity is not a number, it is a notion, a concept, meaning this limiting value becomes unbounded. So it is one of the situations where you say the limit does not exist. So in this case, condition 1 also fails. And because you don't have the left-hand side and the right-hand side of the equation, there's no way you can talk about what it means by left-hand side equals the right-hand side. So all 3 conditions fails for case 3. Now case 4. So here you can see from the graph, this function is not defined as c, it's just an empty circle. There's nothing along the line x equal to c, right? So we do not have f of c. So condition 2 failed. All right, so by knowing this, we can already say function is not continuous at x equal to c. Okay, but I want to kind of like go through all 3 conditions so that you can see more information. In this case, if we look at the limit of f as x approaches c, you can see that if x approaches c from left to right, function values go this way, right? And if x approaches c from the right to left, function values go this way. And again, they meet at wherever this empty circle is, as you can see on the graph. So in this case, it exists. Okay, and again, because I don't have the right hand side of the equation, therefore I cannot say what it means by L equals something that doesn't even exist, okay? So you also don't have condition 3, so that's it. Here, our last one. We see a solid dot here, that is f of c, okay? So condition 2, check. We have f of c defined. Condition 2 I have. Now we look at the limit as x approaches c. You can see that the function values, they meet where the dot is, and that's called the dot, the height of the dot, L, okay? And you can see L is the same as f of c. So the limit exists, so condition 1 check. And from the graph, I only have one point here. I have L equals f of c, or you can say the limit of f of x as x approaches c equals f of c. Okay, so this is now condition 3, refers to the equality here. Okay, so finally, case 5, we do say f is continuous at x equal to c. Okay, so now let's look over the graphs again. All right, and let's think about just English. Forget about mathematics. If I want to say that a curve is continuous, you're drawing a curve. You want to say a curve is continuous. It's like you can just draw it this way, right? Without lifting your pen or pencil, right? It goes like continuously like that, right? If you just think about English, okay? All right, so now let's go over the example 1. If I am drawing the function, I go this way, then I must lift my marker and continue from here. So you can see the action is being interrupted. So intuitively, you can say the function is not continuous at x equal to c, right? And similarly, case 2, I'm traveling from the left. Okay, keep in mind this is an empty circle, so I cannot just keep going. For me to go from the left to the right and then mark f of c, I have to jump up. Okay, so I have to lift my marker and go this way and then continue to the right. So again, the motion is being interrupted. So it's not continuous at this point. Same for case 3. You can see if I travel from the left, as it keeps going up and up, I can never cross this dotted line. It's called the asymptote, vertical asymptote. I can never cross this. So again, I can't just continuously travel to the right hand side. Okay, case 4. I travel from here and I go. Okay, suppose I'm driving on the highway. Boom, there's a hole. There's a hole here. So I cannot just keep driving because I will fail. So I must lift my marker and then have a jump. Then I can continue. So I'm being interrupted. Function is not continuous at c. Okay, it's being interrupted. Okay, over here, I can just go like that without any interruption. So like intuitively use English, you can see like if I'm driving on this highway, I can drive continuously without interruptions. Okay, so this is what it means by f is continuous at x equal to c, and we have rigorous mathematical definition that is this: the limit must exist, the function must be defined at c, and the limit value equals the function value. Okay, so I'm going to erase this so that I have someone to write. If you need to pause the video, please pause it. I'm going to erase some of the board. So let us look again. The definition or the condition for f being continuous at c. Okay, so f of c is f at c. Okay, the f value at c. The left-hand side of the equation is the nearby behavior or nearby f of x behavior. Apparently I cannot spell. Let me do it again. Behavior, nearby behaviors of f around c. You see, the left-hand side and the right-hand side, they're talking about two different things. And only when the nearby behaviors match what happens at x equal to c, then you say the function is continuous at c. And on graph, what you see is you can travel continuously along the curve without any interruptions. Okay, so mathematical rigorous definition, intuitive way to see whether f is continuous at c. All right.